Okay, so we are in lab 9. Lab 9, ANOVA, because we had lab 8, which was the repeated measures. And so what I would like to do today is to kind of dive into this and not go through this line by line by line like we've done in the past, and just really assess ANOVA from a common sense standpoint. And so what we have been looking at up until now is a design that has two comparisons. And what we will do today is we're going to add one extra group to our comparisons. So as an example here, does drinking alcohol decrease math scores? And I've looked at this example before, but we really haven't performed an analysis with this example. As we know, the independent variable is the different conditions, drinking or water conditions versus coffee and alcohol. Those are the levels right there, I should say. And the condition is what the person is drinking. That's the independent variable. And then we have those three levels: water, coffee, and alcohol. With that in mind, if we were to do several t-tests with this, the problem that would happen is that you would have a family-wise error. So you would have an alpha for this group, an alpha for this group, and an alpha for this group. And essentially, you're comparing all three groups, but you would have a 15% family-wise error. That's the mathematics involved in that. I'm not going to go into too much detail of why this is. It's not really necessary for this course, but just know that if you were to do individual t-tests, you would have this problem. So with that in mind, there's a special way in which we can analyze all three of these groups, all three of these samples right here, which are representations of the population. So we are going to do a one-way between groups ANOVA. What does that really mean? Well, first things first, it's starring variances. We're looking at variances, and essentially we're still looking at means differences, but we're adding the extra idea of variances. Before I go into what variances is and just some details about it, there's some terminologies. There's some other terminology I would like to explore. Factor. This is an independent variable that designates the groups being compared. And then we have levels. We've already seen this before. Conditions or values that make up a factor. And then we're going to be dealing with a factorial design. Maybe not for today so much because we only have three groups, and it's there's three levels. I mean, there's one independent variable with three levels, is what I mean to say. And the levels represent the groups, but it's not like we have two different types of changes that are being made. One independent variable with one change element or one treatment element, which is broken down into three levels. If we were to have two change elements broken down into levels, then that would be a factorial design. When you have two or more independent variables in your ANOVA, that would be a factorial design. We're going to just glimpse into that, but what we will be doing is a one-way ANOVA, which is a lot simpler. So what do we have here? I'm going to go ahead and move into this. So this is a one-way ANOVA example. So we have our independent variable, and the independent variable is the type of drink, and then the levels is water, coffee, and alcohol. And we're trying to see if there is a means difference in their math score. So we give them water. One group gets water, one group gets coffee, and one group gets alcohol, and then they're tasked to complete a math test. and then their mean math scores are compared, and that's sort of the crux of this analysis or this example of a one-way ANOVA. Now, what we could add is a different independent variable, an additional one, not a different one. Well, it is different, but it's an additional one. So you could say, well, the type of drink is one treatment, one change that we put into this experiment. It's a controlled experiment. Everything stays the same between these groups besides one factor, and that is the type of drink. Now we're going to change another factor, which is the amount of drink, 1 cup versus 2 cups. This is the second change agent. This is the second factor that's being changed in the experiment, and this is the first factor that's being changed in the experiment. So with that in mind, let's go ahead and move on. And what we see here is if we had these two independent variables, amount of drink, which has 2 levels, 1 cup and 2 cups, and we have type of drink, which is 3 levels, what we have here is we would need to create a factorial table. I don't know if this is an official way of saying it, but that's how I'm going to describe it. Is we have a 2 by 3 two-way ANOVA where we have 2 levels and 1 variable, amount of drink, that's 1 independent variable, 1 cup, 2 cups, by 3, type of drink is the second, or actually it's the first variable, independent variable. Really, if I was to write this as I drew it right here in this model, this would be a 3 by 2 because we have 3 levels of the first independent variable and 2 levels of the second independent variable. But what is usually done is the smaller number goes first and then the larger number goes second. So hopefully that's not too confusing, but let's move on. So what we have here is a table that looks at all the various conditions that will come up in this experiment. So there is the water condition, and in the water condition, it will intersect with the drink condition. In this case, 1 cup versus 2 cup. And so you have 1 cup of water, 2 cups of water. I guess a better way of saying this is the amount of drink condition is going to intersect. Sorry, this is the amount of drink conditions. The amount of drink condition is going to intersect with the type of drink condition. And so we have the first level of the type of drink condition intersecting with the first level of the amount of drink condition. And then we have the first level, or we have the first level of the type of drink condition intersecting with the second level of the amount of drink condition. And so on and so forth, as we see here. And we would test all these conditions, and we would compare them, and that's how we would perform this two-way between groups ANOVA. What we will be doing is a lot simpler, but just putting it out there. We can probably have a discussion later on this, but wanted to just show you this because it's part of the plan here. As we see, you know, we have this description the walkthrough provides. And this is the plan that we're going to go by, is what this walkthrough provides. What we will be dealing in today, when you're going to be answering your questions today for your homework, is a one-way between groups ANOVA, where we just have 1 independent variable with 3 levels, and we're comparing their outcome, their dependent variable scores on, let's say, a math test, or maybe this is a math quiz. I'm not sure if it's a math test or math quiz. So what do I mean by variability? So there is going to be things that are going to change, that will change throughout an experiment, and we wish to have there to be change when it comes to the independent variable. So we wish that there will be change when it comes to water versus coffee versus alcohol. That's what we expect there to be a change in, and this is what's known as systematic treatment effects. Of course, if you give somebody enough alcohol and compare them to somebody with drinks enough coffee and then somebody who drinks water, they're going to, generally speaking, on average, a group is going to act differently on alcohol versus water versus coffee. But what is not anticipated is when we're comparing groups between treatments variance, when we're comparing groups, there's also going to be some random error involved. Just error that we don't anticipate. It's white noise. It's just something that happens. There's never going to be a perfect situation where we can control all factors in the experiment. There's going to be random error. And that goes on the top of this F ratio that we will be looking at a little bit later. On the bottom of the F ratio is the within group treatment variance. What do I mean by that? So there's going to be some unanticipated, unsystematic factors or random error that you're going to have within the subject. So if I'm to move this along, and I think I have a nice picture to go with this, I'll go with a picture. And I did that. Okay, so we have these different groups, and that's represented between. Now, within this part right here is there's going to be some individual differences. So, like, some people can really, really handle their alcohol, right? They're very stoic, or maybe they get really silly when they are on alcohol, or maybe they're very happy when they're on alcohol. I mean, the people have different effects when they're on alcohol. It's not going to be across the board the same within a group. So even though you have this, they're exposed to the same treatment within that group, there's going to be some random differences that you'll see within that group. And we hope that this is going to be very small. We also hope that this random difference is going to be very small. And we hope that the systematic difference is going to be very large. So here we go. So we have between group variance and within group variance. We want this to be very big, right? So we want this to be, I don't know, 7.7. And this to be maybe 0.00001, right? We don't want this to be factored in. But we also want this one to be very small as well. If this was very large, like this was, I don't know, 10, right? Just, you know, if we were to do the math here, and I'm just going to move this along here. If we were to just like say, well, we have the situation where 7.7 divided by 10, right? It's going to be 0.77. And I probably should have known about that. I should have known better. You know, this is kind of the problem being a psychology, you know, in the psychology department. It's like we don't really deal with math that much, but we're going to move forward. So yeah, it's going to be a very small number. We want a very large number, right? So like if I'm to move here, I'm going to move right here right now. Right. So your F value is kind of like your T statistic, but there's no like two tails to it. Just know that there is going to be a critical F value, and there's also going to be a T statistic that is appropriate. So if you have a T statistic that is 3.68, you're usually going to get a P that is less than 0.05. You're usually going to show your P-value is really going to reflect there's a significant difference between the groups.